Okay, today we want to discuss the normal distribution. The normal distribution, also sometimes called the Gaussian distribution, is an extremely important distribution function, um, especially when we're talking about most processes where we're doing things like making measurements, making repeated measurements of behavior or properties of a group or a category. So the normal distribution is an important distribution function. This is really what everything that we've talked about and done so far in probability and statistics leads up to. Now, in this lecture, I'm just going to do a very brief overview of the normal distribution function because, first of all, the materials as presented in your textbook and given in these slides are not super good. And secondly, what you really need to see are a number of worked example problems where we utilize the tables in your textbook. So I will just do a brief introduction, and then the additional information in this chapter will be some written materials where I provide you with some worked problems and some explanation of what you do with the various tables in your textbook. So the normal distribution or Gaussian distribution function is defined as the distribution with the following density function, where sigma is the standard deviation and mu is the mean. It's actually a relatively straightforward function. If you look, this is an example of what the normal distribution looks like with a mean of 0 for various values of sigma. So mu is the mean and sigma is the standard deviation. This constant factor that appeared at the beginning of the distribution function is there to normalize the distribution function so that when you integrate the area under the curve from minus infinity to infinity, it's equal to 1. That's required, basically, that if an event occurs, and this is its probability density distribution function, when you integrate this, it's got to be 1 to say that somewhere under this curve the event occurred. The curve is symmetric with respect to x equals mu, the mean, because the exponent's quadratic. So for mu equals 0, it's symmetric to the y-axis. And this is where the famous expression, the bell curve, comes from. The exponential function goes to 0 very fast, a lot faster. In fact, the smaller the standard deviation, the faster the function goes to 0. So a small standard deviation would mean that your probability is pretty compactly found. A large standard deviation means this curve is short and fat. So the distribution function then, which is the integral of the probability density function, is found by integrating the following, and when you place x as an upper limit of the integral so that you can get f as a function of x, they've used the dummy variable here. You can also standardize the normal distribution function, meaning you basically shift the curve such that it's centered about the origin, and you define a standard deviation of 1. And so if you do that, then you get this normalized expression. This is pretty commonly done. It's basically just a shifted scaled function. The reason that you do that, and yes, I'm aware that you can have a data set and find its standard deviation and it will rarely be 1, but what you do is you scale the function so that it is 1, so that all your tables are common. And then after you do your computations and your calculations and your comparisons, you go back and you correct for the fact that the standard distribution is in fact, or that the standard deviation is in fact not 1. So it's kind of like, we scale it and shift it so that we can use appropriate tables or computational methods, and then we scale and shift it back to apply to our actual problem. So this is not integrable in closed form, So basically, this is tabulated, and in your textbook, in Table A7, in Appendix 5, you have the tabulated values, and then any decent software package on the market today will also give you the value of this integral for a given x based on a lookup table. So here is this phi of x, this normalized distribution function. Basically, it just means that it's centered about 0. So at 0, which would be the mean, the normalized mean, you would have a value of 0.5. And then you're going to approach 1 for your final value. You approach 0, and your variance is 1. So you can see when you're at 1 and minus 1 what percentages you fall at. The reason that this is useful is that table A7 relates directly to the standardized distribution function phi of z, where z is a shifted scaled variable. So if you define z as x minus u over sigma, then that enables you for a normal distribution function, sorry, no pun intended, for a distribution function f of x to use the tables in the textbook. You can find the probability that a normal variable with mean mu and standard deviation sigma will occur within an interval b and a by taking the difference in the standardized functions. So at this point, I'm going to stop and just say a couple of things about normal distribution functions, and then refer you to the notes that go much more in detail about how to apply these tables. So first of all, normal distribution functions define most things in nature. And what they don't define is usually because there's a limited sample size. So if I were to take your class and I were to look at the distribution of grades on any given exam, that would be pretty close to a normal distribution. The larger your class size became, the larger your population, the more closely we would approximate a normal or a Gaussian distribution. Or, like similarly, if I gave you an infinite number of exams and averaged all of the distribution functions together, then that average of distribution functions would look like a normal distribution or a Gaussian distribution. And we describe that phenomenon with the theorem known as the central limit theorem, meaning you sample enough, either enough times averaging distribution functions or large enough sample space, and you will ultimately approach a normal distribution. So that's the central limit theorem, and it's really key to a lot of things, both in engineering as well as in statistics. The other thing about the normal distribution is that many comparisons between groups with very basic fundamental statistical testing, which is what we will discuss in our next series of lectures, many comparisons between groups assume a normal distribution function. So when you make statistical inferences about groups being different or events having a certain probability of occurrence, etc., most of the time you're layered on top of the assumption that you have a normal distribution function. Not always, but most of the time. So we're going to talk about the statistical t-test, the student's t-test. And when we talk about that, you need to understand that the assumption is that the distribution is a normal or Gaussian distribution. So part of what you'll do on the project is look at a distribution of numbers for two different groups and determine, first of all, are there outliers? Secondly, how close it is to normal. This is another reason that the identification of outliers is important, because the presence of outliers can take what might be a normal distribution and skew it in such a way that it's no longer normal. So we will talk a little bit more about that in some supplemental material that I'll add when we talk about statistical testing.